Hello everyone, this video is about three-phase full converter FET DC separated center motor. The three-phase full converter is a two-quadrant converter which can do two quadrants of operation to DC motor. It is possible to obtain either forward working mode or reverse braking mode. The armature of the motor is fed by full converter. The field winding is connected to a constant DC source. The variable output voltage from the converter will provide the speed control of the motor by armature voltage control method. The circuit of this is shown here. It has 6 thyristors. The thyristors are numbered in the order in which they are triggered. There are two modes of operation of the circuit, continuous conduction mode and discontinuous conduction mode. Both these modes can operate in both the rectification and inversion modes. For firing of a less than 90 degree, we can get the rectification mode of operation, and for firing on a more than 90 degree, we can get inversion mode of operation. Now let us see the continuous conduction mode. In this mode, the armature current is always non-zero. The devices are numbered in the sequence they are triggered. At any time, there are two devices conducting, one from top and another one from the bottom. The interval between each triggering will be 60 degrees. Each device will conduct forward 20 degrees. Hence, when T1 is triggered, it will conduct along with the already conducting device, which will be T6. Hence, the armature will be connected between the terminals A and B. So, the armature voltage will follow VAB. And after 60 degree interval, T2 is triggered. When T2 is triggered, it will conduct along with T1. At that time, T6 is turned off. And the armature is connected between the terminals A and C. Hence, the armature voltage will be equal to VAC. The below table shows the different devices that are conducting and the corresponding voltage. When T1 is triggered, T1 and T6 combination will conduct, which will make VA equal to VAB. When T2 is triggered, T2 and T1 will conduct, hence VA will be equal to VAC. Then at a 60 degree interval, T3 is triggered, so T3 and T2 will conduct, hence the voltage VA will be equal to VAC. When T4 is triggered, T3 and T4 will conduct, which makes VA equal to VBA. When T5 is triggered, T4 and T5 combination will conduct, which makes VA equal to VCA. And when T6 is triggered, T5 and T6 will conduct, which will make VA equal to VCP. If the diagram of the line and the phase voltages are given, VAN is taken as the reference voltage. Hence, we can represent the phase voltage VAN as VMP sin omega t, VPN equal to VMP sin omega t minus 2 pi by 3, VCN equal to VMP sin omega t plus 2 pi by 3. The corresponding line voltages are given by VAB equal to VAN minus VBN, which is equal to VM sin omega t plus pi by 6. VBC equal to VBN minus VCN, that is equal to VM sin omega t minus pi by 2. VCA equal to VCN minus VAN, which is equal to VM sin omega t plus 7 pi by 6. That VM is equal to root 3 into VMP. This is the phase voltages and the different switches which are forward biased. So when VAN is more positive, T1 is forward biased. When VAN is more negative, T4 is forward biased. T3 is forward biased when VBN is more positive, and T6 is forward biased when VBN is more negative. T5 is forward biased when VCN is more positive, and when VCN is more negative, T2 is forward biased. And we have noticed from the table that the armature voltage follows only the line voltages. So in order to draw the armature voltage, we will be considering only the line voltage wave. Now let us see the waveform for the armature voltage for firing angle alpha equal to 60 degree, and this is the waveform for VA for alpha equal to 60 degree. For drawing this waveform, we have considered only the line voltages, and all the line voltages are drawn in the positive side in order to draw the output voltage waveform. So VAB is drawn here. The negative part of VAB is drawn as the mirror image, and it is denoted as VEQ. Similarly, VBC is drawn after 120 degree interval here, and the negative part of VBC is drawn here as VCB. And from VBC after 120 degree interval, VCA is drawn, and the negative part VCA is drawn. The negative part here, it is drawn as the VAC waveform here. So we are going to trigger T1 at alpha equal to 60 degree. The alpha is measured by taking the natural point of flickering 5/6. From this 5/6, we have to measure 60 degree and trigger T1. When T1 is triggered at this point, T1 and T6 combination will conduct, which will make VA, that is armature voltage, equal to VAB waveform. Hence, the armature voltage will follow VAB waveform when T1 and T6 combination are conducting. Then, after 60 degree interval, T2 is triggered here, after which T1 and T2 combination will conduct. Hence, the voltage, armature voltage will follow VAC waveform. Then when T3 is triggered at this point, T3 and T2 combination will conduct, which will make VA to follow VBC waveform, and so on. Similarly, we can draw the armature current, which will be always greater than 0, and the armature current IU is shown here. So these two waveforms are the armature voltage waveform. The darkened portion is shown here, which is the armature voltage waveform, which is nothing but the output voltage of the three-phase converter, and this is the armature current waveform. And this waveform is drawn for alpha equal to 60 degree, which comes under rectification mode, and this is nothing but denoting mode of operation. And similarly, we can draw the armature voltage waveform for alpha equal to 120 degree, which is nothing but the inversion mode for breaking of operation. So for drawing the output voltage, that is armature voltage for inversion mode, we have taken the line voltages in the negative directions. So we have to trigger T1 at this point from the natural point of triggering, measure 120 degree, and we have to trigger T1 at this point. So when T1 is triggered, T1 and T6 combination will conduct, which is allowing VA to follow VAB waveform. So VAB waveform is here. So it is going to follow VAB waveform. When T2 is triggered, T2 and T1 combination will conduct. So VA will follow VAC waveform. And when T3 is triggered, T3 and T2 combination will conduct. Hence, VA will follow VBC waveform. So when T4 is triggered, T3 and T4 combination will conduct. Hence, VA will follow VBC waveform. All these things are taken from the table which is already shown. The corresponding armature current is shown here. Since we have considered the continuous mode of operation, the armature current is always greater than 0. So this waveform is nothing but the armature voltage and current waveform for alpha equal to 140 degree, which is nothing but inversion mode or breaking mode of operation. I will out and drawing the voltage waveform. I will provide the link for drawing the voltage waveform for rectification and inversion mode of operation in the description box. Average armature voltage is derived here. The average armature voltage VA is equal to 6 by 2 pi integration from pi by 6 plus alpha to pi by 6 plus alpha plus pi by 3. Why 6 is present here is that in the armature voltage there are 6.6% in per cycle. And the integration limits are from pi by 6 plus alpha to pi by 6 plus alpha plus pi by 3. VA d omega. Now VA from pi by 6 plus alpha to this pi by 6 plus alpha plus pi by 3. That is, this is the duration during which T1 and T6 combination are conducting. Hence, VA will be equal to VAB expression. And we know that VAB is equal to Vm sin omega t plus pi by 6. So substituting for VA, we will get this expression. Then armature voltage VA is equal to, after integration and substituting the limits, it will be T Vm by pi minus cos 2 pi by 3 plus alpha plus cos pi by 3 plus alpha. After simplification, the average armature voltage will be equal to 3 Vm by pi cos alpha. The speed torque equation of the DC separately excited motor is given by omega m equal to VA by K minus TRA by K square. Substituting for VA as 3 Vm by pi cos alpha, the speed expression will be 3 Vm cos alpha by pi K minus TRA by K square. The above relation gives the speed torque equation of the DC separately excited motor, which is fed by 3-phase pull converter. And we have considered the mode as the continuous conduction mode. And after operating the converter both in rectification and the inversion mode, the speed torque characteristics for rectification and the inversion mode will be like this. For alpha less than 90 degree, we will take the first quadratic operation, that is forward moving mode. And for alpha greater than 90, we will get the inversion mode, that is breaking mode of operation of the DC separately excited motor. Now it's time to see discontinuous conduction mode of operation. In discontinuous conduction mode, the armature current is not continuous. The armature current reaches zero before the next device of the converter is triggered. When T1 is triggered, it will conduct along with T6. The armature is connected between the terminals A and B, and the VA will be equal to VAB. At omega t equal to beta, the armature current reaches zero before T2 is triggered. From beta to the next instrument triggering, no device will be in on condition. Hence, the armature voltage will be equal to the back EMF E. This table shows the devices that are conducting for different periods and the corresponding armature voltage. From the period pi by 6 to pi by 6 plus alpha to beta, T1 and T6 combination will conduct, which will make VA equal to VAB. From beta to pi by 6 plus alpha plus pi by 3, no device will be in conduction, hence VA will be equal to V. From pi by 6 plus alpha plus pi by 3 to beta plus pi by 3, T1 and T2 will conduct, which makes VA to follow VAC waveform. From beta plus pi by 3 to pi by 6 plus alpha plus 2 pi by 3, no device is number, and VA will be equal to E, and so on. So this table shows the different devices that are conducting and the corresponding VA voltage for one complete cycle. The average armature voltage for this case is derived here. VA is equal to 6 by 2 pi, pi by 6 plus alpha to pi by 6 plus alpha plus 2 pi by 2 VA given by VA. And the VA voltage is equal to VAB from pi by 6 plus alpha to beta, and is equal to V from beta to pi by 6 plus alpha plus 2 pi by 3. After integration and substituting the limit, the expression for VA is shown in this equation, and rearranging the term, the VA expression is given in this expression. Substituting this VA expression in the speed expression, omega m equal to 3 by pi Vm cos pi by 3 plus alpha minus cos pi by 6 plus beta plus E into pi by 2 plus alpha minus beta divided by K minus T RA by K square. Now in the speed expression, the back EMF term should not be correct because back EMF is also dependent on the speed. Hence, substituting for back EMF equal to K omega L and rearrange the above expression, we will get the speed expression for the motor as omega m equal to 3 by pi Vm cos pi by 3 plus alpha minus cos pi by 6 plus beta divided by K into 1 minus 3 by pi into pi by 2 plus alpha minus beta minus TRA by K square into 1 minus 3 by pi into pi by 2 plus alpha minus beta. This expression gives the speed torque equation of the DC separately excited motor fed by three-phase two converter, which is operated in the discontinuous conduction mode. The below graph shows the speed torque characteristics of the DC separately excited motor, which is operated in both continuous and discontinuous conduction mode. This graph shows the combination of both continuous and discontinuous conduction mode. The characteristics which is shown to the left of this dashed line is the characteristics corresponding to the discontinuous conduction mode, and the characteristics that are shown to the right of the dashed line are the characteristics corresponding to the continuous conduction mode. The dashed curve shows the boundary line between the continuous and the discontinuous conduction mode. In order to operate the DC motor in the continuous conduction mode, we need to make the speed of the DC motor to be greater than the critical speed, which is the boundary between the continuous and the discontinuous conduction mode. And this is the characteristic which combines both the continuous and the discontinuous conduction mode of operation of the DC separately excited motor fed by three-phase two converter, which is operated both in continuous and discontinuous conduction mode. Thank you.